Okay, for the next talk, I would like to welcome Professor Pengcheng Dai from Rice University. Yes.
Yeah, I suppose I should thank Chimiao and Yunlong to assign me for this talk. Yeah, so there's actually some result that we haven't published yet. Talk about the string tuning of anomalous Hall effect in this very interesting outer magnet, manganese hexagonal manganese tellurium. And this was actually done for more than about a year in our group. And I'm also going to talk a little bit about the very recent result that we just posted on the archive. When you dope lithium, what actually happens to this outer magnet. So the first, let me introduce the first part of the talk is mostly done by a talented graduate student, Shijie Xu, and then sort of a former postdoc, Zhao Yu. Now he had moved on, and then with undergraduate Shi Yu and Ting Jun. And then we've been very fortunate to collaborate with Junhao Chu. We basically sort of, Zhao Yu used to be a postdoc with Junhao's group, so he basically imported the entire sort of ability to do transport measurement and the string to our group. And then we did a little bit of stability at the University of Houston, and then we did a lot of the neutron scattering at the Oak Ridge National Laboratory and some high field measurement. And then Raphael is our sort of a theorist in this problem. So let me sort of give a very brief introduction of what is a sort of outer magnet, and then I'll try to show our result in terms of how we actually use neutron scattering and the unilateral string to actually to sort of detune the sample, really make the sample into a single magnetic domain in order to actually separate its intrinsic magnetic and transport properties, and then I'll show our transport measurement in terms of how a string tuning can actually change the signs of anomalous Hall effect. Basically, what we're actually claiming is that at a particular sort of a temperature range, that the unilateral string can actually sweep the direction of sort of Hall vector from upper to down state. And then finally, I'll conclude on this prospect on this project, and then I'll talk about what actually happens in the case of lithium doping. So let me give a very sort of extremely simple example of introduction of sort of a simple ferromagnet. A simple ferromagnet was known sort of a few centuries ago in terms of sort of a simple ferromagnet. All the spins are lined up together. If you look at it in sort of a reciprocal space, and then your magnetic Bragg peak would occur at exactly q equal to 0. And then if you look at the electronic band structure for such a system, then you should expect the spin bands will be sort of split. You have a spin minority band and spin majority band, and then you'll be a spin flop transition, and the electronic band will be sort of a split like this and be a S wave. In the case of a simple antiferromagnet, here I'm strictly talking about a simple collinear antiferromagnet on a simple square lattice. You would expect the new vector in this case is going to be the finite momentum transfer Q, because your unit cell have doubled in both A and B direction. And if you look at the spin wave in such a situation, or electronic band in such a situation, in this case, you basically have a translational invariant and a rotational invariant, and you should expect the electronic bands between spin up and spin down bands to be sort of a completely degenerate. And then in this case, if you look at spin wave for such a system, then you should expect the spin wave in terms of left rotating and right rotating also to be completely degenerate. Therefore, there's actually no differences. Whereas in the case of a simple ferromagnet, it's only rotating counterclockwise. So the claim of sort of a recent claim of outer magnet is particularly in this context is a system in which is strictly still a simple collinear antiferromagnet, except that the translational symmetry is sort of obeyed, but your rotational symmetry is actually you need to rotate your local environment to be 90 degrees in order to repeat itself. And then the band structure calculation in such a situation will suggest that you would have spin up and spin down band split some portion of the reciprocal space. And this is in terms of electronic band. If you simply think about in terms of spin wave bands, naively, if the system is completely collinear, and then again it should be completely identical to the case of a collinear simple antiferromagnet, where spin wave should be left rotating and right rotating should be completely sort of degenerate. Especially if you think about the spin wave are completely arises from a dipolar interaction in which the exchange coupling only depend on the distance, because the distance between this and this and this is completely independent of your local environment, then therefore you should see essentially no difference as compared with a system that's a strictly collinear antiferromagnet in terms of spin waves. So now let me think about tell you a little bit about what is really expected to be sort of different. So as I sort of mentioned earlier, that in the case of a strictly a simple ferromagnet, you should expect the electronic band to be split, and then spin band to have up and down state, and then a time reversal symmetry is broken, and then everything is basically S wave. In the case of a simple strictly collinear antiferromagnet, and then your electronic and spin wave band should be degenerate, and then you shouldn't have a time reversal symmetry breaking. And finally, in the case of a sort of a so-called outer magnet, you should expect to see a sort of a split of the band in partially some region of the reciprocal space. And in this case, the system would essentially behave could potentially behave as a simple ferromagnet, and yet the overall magnetization is still tiny. So the question is whether that real material sort of behave like this and would exhibit interesting magnetic and transport properties. So I mean, when Neil discovered sort of his famous antiferromagnetic order, he actually, this is one of the statements he made that sort of interesting, but not sure what is actually used. But nowadays, all the hard drive use sort of spintronics, and in this case, one of the major problem is sort of the street field. If you simply think about a simple ferromagnet, and ferromagnet, because it's a dipolar interaction, would exhibit a fairly large stream field, but in the case of an antiferromagnet, you would not have that. So the question is whether outer magnet would have a property that combine both sort of a ferromagnet in terms of giving rise to ferromagnetic properties, but yet it doesn't actually have sort of a very large stream field. So the first prototypical sort of example of outer magnet is this sort of a famous ruthenium dioxide, and this material was, at least in thin film form, was found to exhibit some sort of anomalous Hall effect, and people, thought, oh, this may be a first example of outer magnet. But at least, subsequent measurement have shown conclusively, at least in bulk, this material, there's just basically no magnetism. So therefore, there's this really is now basically confirmed to be not really in sort of outer magnet. And the other example believed to be a outer magnet is the situation of a chromium antimony. And in this case, the system is actually a hexagonal. It's collinear, but with the moment along the z-axis direction. And in this particular geometry, that you actually do not expect anomalous Hall effect. And neutron measurement have shown a band splitting, suggesting it could be a sort of an outer magnet. But the most interesting one, in my opinion, is this so-called hexagonal, the manganese tellurium. And the reason this particular sort of system is very, very interesting is mostly because the fact that even though it has the same magnetic structure as sort of a chromium antimony, but in this case, the actual moment is actually in the plane. And it has been shown through outer magnet, sort of a magnetic space group argument, in this sort of a magnetic symmetry, you could, in principle, have anomalous Hall effect, and yet the system have a very little, magnetization and very little, ferromagnetic component. And let me sort of basically give like a one-page introduction as in terms of what is sort of the transport signatures of anomalous Hall effect. And before I do that, let me show you, what is a typical Hall effect. Let's just say that, for example, we have this a very simple metal, and when we put a current through it, and then when we put additional magnetic field perpendicular to the current, you should expect to see a Hall voltage in the direction perpendicular to the current direction. And this Hall voltage basically is what we're measuring in this particular system. And when it's a simple pure metal, then you would expect that when you turn off the current, there will be no Hall voltage. So what is anomalous Hall is basically saying is you have a conventional Hall effect, but in addition you have additional contribution to the Hall voltage, even when there's no additional external magnetic field applied to the system. And this is what typically we're contributing as an anomalous Hall effect. Of course, if the system is, instead of a simple pure metal, but actually a magnetic metal, which, has an intrinsic internal field applied on the system by itself through the magnetic iron, of course, you would have this sort of anomalous Hall effect, and which should be there even when the external field is, reduced to zero. And finally, there's also this so-called topological Hall effect, which I will not, discuss too much here. And the topological Hall effect can have various reasons. One of the reasons is that you have a fictitious field applied on the system, and this could be due to skyrmions and due to other non-zero scalar spin clarity. But like I said, I will not emphasize too much here. So the situation in the case of lutetium dioxide has now been clear. It's not a outer magnet. And the situation in this case, at least in bulk, there's no anomalous Hall. But in this particular compound, magneturium, the anomalous Hall has been observed both in thin film as well as in bulk. In fact, many sort of decades ago, first in sort of the transmol measurement. This paper basically show a very recent measurement. And this anomalous Hall is really anomalous Hall in the sense that it's a spontaneous anomalous Hall. Basically means you can actually see sort of hysteresis loops in terms of your anomalous Hall rho xy. And this basically means it basically behaves like a simple ferromagnet, except the stability actually show the magnetization of the system. This loop is has an exceedingly sort of a small moment. So when we initially, let me give additional evidence for why this system could be a sort of really outer magnet. And transport measurement have suggested that it could be outer magnet, but the other type of measurement suggests it could be outer magnet is angle resolved photoemission spectroscopy show a splitting of the electronic band. But I'll try to emphasize in terms of sort of neutron scattering experiment, actually done not by our group, by a group in Japan, have shown clearly a splitting of the magnon band at some portion between gamma and L point in reciprocal space. Yeah.
Something previous slide. There's something anomalous about this hysteresis loop?
Yes.
Or it's just that there's no order.
Yeah, so the reason it's actually interesting is mostly because the fact that you have this hysteresis loop, and in a strictly long-range ordered antiferromagnet, there shouldn't be any neck magnetization. And the system does have an extremely small neck magnetization. People think it might be a small canting, or it's not completely clear. But yet you have this hysteresis loop for a magnetic field applied along the c-axis.
Hysteresis itself.
Well, it's normal, except for the fact that the moment is exceedingly small. I mean, strictly speaking, in clearly a completely collinear antiferromagnet, it shouldn't be there. Yeah, no. Let me show you. Actually, I mean, that was sort of what's been published. But what we actually discover is that it's actually exceedingly sample dependent. Yeah. So let me introduce to you that why this splitting, and this is not sort of electronic band, but rather a spin wave band splitting. This is actually exceedingly sort of strange. The way this is reason is exceedingly strange is that, as I mentioned earlier, that in the case of a simple a collinear antiferromagnet, you should expect your spin wave band to be left turning, right turning, to be completely degenerate. Because in the case of a spin wave band, that the entire magnetic exchange interaction is due to a so-called dipolar interaction. And dipolar interaction is strictly only depend on the distance of the system. It doesn't really care what is the local environment, which is completely sort of contradicting to naive thinking of an outer magnet. But in this case, if you think about the reason you have this spin wave band splitting, what is actually been shown to be slightly different is that the magnetic exchange coupling between the diagonal direction between this spin and this spin, which is J10, 10th nearest neighbor, and between this spin J11 and J10 is actually different. That's why initially when the PR paper by the Japanese group was published, I actually don't believe it, because in most insulators or metals that your exchange coupling, by the time you go to 3 or 4 J's, it's completely, irrelevant, right, to the system. So when they fit the spin wave spectra and claim the J10 and J11 are different, because the J10 does not pass through the tellurium atom, where J11 does pass, even though the distance is identical. So naively speaking, you should expect in strictly dipolar interaction systems, the exchange coupling should be completely the same. Therefore, you should not actually expect to see the splitting. But in fact, you actually do see the splitting, and that actually, in my opinion, is actually extremely strong evidence that this, local environment, actually matters in terms of, your spin wave band splitting, which is actually a key indication of the system is generally a outer magnet. So now let me, sort of show you the data again. And the earlier plot I showed was data published in PRB like a year or two ago. And in fact, this anomalous Hall, was not new. It was 1965. It's one of those measurements that was really published sort of very, very early. And this was a more recent measurement published 2024. And when we sort of started doing this, when Shijie and Zhao Yu started doing this in the group, and they grew these, manganese tellurium samples, and they couldn't, reproduce this anomalous Hall effect. And in fact, the manganese tellurium is not really a good metal. It's actually in what we call sort of a semiconductor. So they have to look at the, various different samples. Oh, this anomalous Hall, by the way, only appears in a very narrow temperature regime below Tn. Tn for this system is 300 Kelvin. It only appears in a very narrow temperature regime below Tn, and then it disappears at low temperature, which again is very strange, right? If it's a simple ferromagnet, that gives rise to the anomalous Hall, you should actually expect, any sort of a magnetic moment should really sort of persist at low temperatures. If it's some sort of impurities, system, impurity magnetic, moment give rise to anomalous Hall, it should also persist at low temperature, right? There's no reason why it should disappear, but it actually disappears at low temperature. So this is not understood at all what is actually going on. So if you look at from a theoretical sort of perspective of this, the reason you can potentially have this anomalous Hall from outer magnetism perspective, and if you think about the system, a manganese tellurium is actually a simple antiferromagnet that's actually collinear, and if the moment is along the c-axis, then there's no problem, because the moment is going to be up and down as you go along the c-axis. But if the moment is actually aligned in the AB plane, then there's actually a problem. And the reason there's actually a problem is because when the moment is aligned within the AB plane, there are actually two possibilities. Your magnetic structure is actually different in terms of the moment relative to the underlying lattice, which is entirely dictated by the spin-orbit coupling. And from neutron scattering experiment on twin sample, you actually cannot tell any differences. And you can have a situation in which the moment is aligned along the next nearest neighbor, manganese bound direction as shown here. And this would have a magnetic point group to be M prime, M prime, M. And in the other case that you would have a case in which the moment is aligned along the nearest neighbor direction, you would have a M, and M space group. So the only way you can potentially have anomalous Hall effect due to outer magnetism is a situation in which when you do a integration due to the barrier curvature, and in the first case of your nearest neighbor, it's going to be some sort of a G wave when the moment aligns on this. Your integration throughout the momentum space, the barrier curvature will give you actually zero contribution to the anomalous Hall. So therefore, if the magnetic structure is M, M, and M, they should not give rise to any anomalous Hall in this situation. Whereas if the situation is next nearest neighbor, you would expect an anomalous Hall. But this is cannot be conclusively determined because the fact that if the moment is actually aligned in the AB plane, then you have three equivalent rotational symmetry directions. Because the system ultimately is a hexagonal, therefore you basically have three domains. When you add up all the intensity of three domains, these two magnetic structures are completely equivalent. If the sample is not between, you therefore cannot separate which one is actually sort of correct. Of course, you can tune the system to be a D wave outer magnet, therefore can directly induce anomalous Hall. But the amount of tuning you would apply, natural tuning you would apply is actually about 2%. you're just going to crash the crystal before the band structure actually changes. I mean, so that's what is going to happen. So yeah, there are a bunch of measurements. People have published papers look at the different sort of magnetic. You can see clearly 3 different magnetic domains, and they plot out all the sort of with additional magnetic field along the c-axis. You actually can change magnetic domain along the c-axis because you can have up, down, down, up, right? That you can change along the c-axis. But the central issue is that you cannot actually separate which magnetic structure is actually correct. So this is sort of where sort of our group came in. So Shijie initially grew these sort of samples that are very good, has the same sort of new temperatures before, and then our transport measurement and chemical analysis measurement shows really sort of a standard manganese tellurium. And the problem that the first thing we wanted to do is to basically determine what is the true magnetic structure of the system, given that we know the moment is actually aligned in the AB plane. And this is what we have done initially, is to basically have a crystal that cut into a square shape, and then we can apply unilateral string along either the nearest neighbor or the next nearest neighbor direction, and therefore we want to use a force to exert a tiny amount of distortion, and therefore potentially change the 3 domain into a 1 domain within the AB plane, and therefore we can look at the diffraction patterns throughout the reciprocal space and determine hopefully which magnetic structure is actually correct. And this is actually done at Oak on an instrument called the Corelli. So you don't have to sort of know the details, but neutron scattering basically look at a magnetic moment that's actually perpendicular to the momentum transfer Q, and also look at perpendicular to the neutron spin direction, and therefore within these 2 models you should expect the magnetic Bragg peaks to be sort of, you can see 6 magnetic Bragg peak at this sort of positions. And then if you try to detwin it, you can have 2 possibilities. And the first possibility is that if you apply a unilateral pressure in the, say, for example, in the next nearest neighbor direction, and you would expect to see the system changes from this shape into either become a single domain like this or become 2 domain like this by symmetry analysis. If it's this particular magnetic structure, you would expect to be the same, but except now the moment is rotated sort of 30 degrees from the previous case. So our hope is that by doing an experiment with unilateral string, we should be able to look at the entire reciprocal space and compare the intensity changes and see whether we can truly detwin the sample from 3 domain to 1 domain, and then therefore determine the magnetic structure of the system. So if the system is along, if the magnetic structure is along M prime M, you should expect the intensity to change from this into this, because in both cases it doesn't matter what the spin direction is. The overall magnetic intensity is identical in both cases. But if you detwin it, if it's become this, you can potentially, looking at these 6 peaks and look at the intensity change, you should be able to see whether this magnetic structure is correct or the M and M and M magnetic structure is correct. So you don't have to sort of know the details, but we actually have done experiment for string along both the nearest neighbor and the next nearest neighbor direction. So after very, very careful analysis, our basic conclusion is that the magnetic structure is conclusively M prime M prime M, and this magnetic structure is actually independent of which unilateral pressure direction we apply the unilateral pressure. Basically meaning that the magnetic structure is actually fixed relative to the underlying lattice, regardless which direction you apply the string, and the magnetic space group is conclusively M prime M prime M, and that's suggesting that the anomalous Hall effect the seen with transport measurement is really due to the fact that the system is actually an outer magnet. So now let me show you sort of how do we actually discover that the unilateral string on this system can actually tune the signs of anomalous Hall effect in this particular sort of a system, which I thought is kind of interesting. So again, let me show you sort of the earlier result that I've shown you that we have this hysteresis loop, and we reproduced the sort of the hysteresis loop that was shown before. But the problem is that this hysteresis loop that we have found in these earlier samples is not completely reproducible, in the sense that we look at the samples. So we look at actually totally. I mean, this is at an earlier slide. We actually look at total 13 samples. It turns out only like 5 samples shows anomalous Hall effect, and it turns out this anomalous Hall effect samples are only shown in samples that sort of are sort of semiconducting with a sort of a charge gap roughly around 15 or 18 millielectron volt. And 15, 18 millielectron volt is roughly around room temperature, or 200 some Kelvin in terms of its energy scale. And that really suggesting to us that this anomalous Hall effect is not only associated with the material itself, but also associated with impurity doping onto the system, so that your charge gap is roughly around this sort of regime, and that's the only case you actually see anomalous Hall effect in this system. And then we mounted the sample onto a piezo sort of electric system, and then start to do sort of a anomalous Hall effect. And what we see immediately, it's actually sort of transformative, is that in the case of a zero string, we see this hysteresis loop. But when you apply a string that to detune the sample into a single magnetic domain, you see this hysteresis loop immediately become exceedingly sharp. And this is actually done on the same sample. And what this actually is suggesting to us immediately is that when you put a unilateral string, you actually detune the sample, and therefore making a single domain sample, and therefore all the green boundaries typically are there in a 3-twin sample that would not contribute to an anomalous Hall. Suddenly disappears, and therefore your anomalous Hall effect become much sharper. Your cohesive field become sort of a much less. And what's even more interesting is that so the additional detail is that the sample, when it's actually mounted on a titanium stage, and then when it cool down intrinsically has some temperature dependence, we're actually taking into account all of this effect. So what's even more interesting is that if you look at the anomalous Hall effect as a function of a temperature, you can see at high temperatures it's sort of behaving in one way, but in the temperature regime, roughly around 230 to roughly 240 Kelvin, this anomalous Hall effect, this hysteresis loop that you actually seen, actually we find that actually changes sign. For example, in this case, the loop goes clockwise. And then at the same temperature, as you gradually apply a unilateral string from from negative, which is compressive, to positive, it actually changes sign, become looping around the other direction. So this is actually a very strange. I mean, anomalous Hall effect changes sign in a regular system as a function of temperature. That's not is not really surprising, because for any sort of multi-band system, you can have electron hole concentration that can be sort of different as a function of temperature. Yet, as a function of a temperature, as a function of unilateral string, it changes sign. Not too many systems actually, behave like that. I'll show a system that does behave like that, later. But I'll argue that the microscopics are actually quite different. So we've, completely mapped out the sort of electronic phase diagram in sort of this regime, and we found is that this anomalous Hall effect changes sign only in the temperature regime. Roughly around 230 Kelvin, and this is actually the temperature regime. If you remember, very similar to the temperature regime where we actually see anomalous Hall effect when the charge gap roughly equals to that. So then this is sort of a further data shown, and also the other thing that we found is that now the anomalous Hall, can extend to much larger temperature range than we will see, in the scroll sample. Like I mentioned earlier. The sample on the twin and the bulk sample only show anomalous Hall, roughly between 300K, below 300K to roughly 200K, and now we can see anomalous Hall all the way down to like 30, 40 Kelvin. And this is sort of the phase diagram that was mapped out, and as compared with the grown sample like this, now we can see anomalous Hall in a much bigger temperature range. Basically, indicating that all the green boundaries has been sort of eliminated. And we thought, to compare this with a situation of anomalous Hall that's been seen in other magnetic systems. Let me try to argue why it's different. unilateral string can changing anomalous Hall effect in terms of a sign change actually has been seen before. For example, it has been seen in the manganese 310 and a few other sort of systems. So when you put a unilateral string, you can actually change anomalous Hall. But in this situation, the system is actually quite different. And in the case, for example, manganese 310, your magnetic structure is actually non-collinear. And not only is non-collinear, it's non-coplanar. That basically means that when you put a unilateral string, you actually can induce a very, very, a small, a non-zero scalar spin polarity. And therefore, your anomalous Hall effect is basically what typically we call, a piezo-magnetism effect. Basically, due to the fact that you have, a spin-lattice coupling, when you put a unilateral pressure onto the system, you're actually changing the local symmetry, and therefore you change slightly the exchange coupling, and therefore you change the spin system. Therefore, the anomalous Hall is actually due to, purely what we call, piezo magnetism, and because the magnetic structure changes slightly. And whereas in the case of alpha manganese tellurium, your piezo magnetism is actually 3 orders of magnitude smaller as compared with for example, manganese sort of 310, and the amount of pressure we can apply is like 0.1 or 0.2 sort of a percent of the system, and you can basically see the nil temperature doesn't change, and then this effect is actually much smaller, basically 3 orders of magnitude smaller. And you can see that in the case of manganese 310, it's roughly 10 to the -3, and here is at 100 megapascal, it's 10 to the -6. So it's very, very much unlikely due to the anomalous Hall effect change, due to the piezo-magnetic effect. And this is additional data that shows that how much time I have? Yeah. So this is additional data shows that what sort of regime in terms of this anomalous Hall effect that we're seeing, as compared with all the other sort of known systems which exhibit anomalous Hall, for example, iron germanium, manganese 3, and manganese tin. Iron 3 tin 2, and all these systems. And the system we're actually seeing is basically in what we typically call sort of the Hoping regime, except it's in the Hoping regime with sort of a exponent that's actually very strange. It's not really sort of understood. So what have we learned? So we have learned that in the case of pure manganese tellurium, the anomalous Hall effect can only be seen when the charge order of the system is not the charge order, charge gap of the system is roughly around 18 millivolt. That basically means that the fact that the system is actually a semiconductor is actually exceedingly important in terms of where you can see anomalous Hall. And second thing we have learned is that the anomalous Hall effect in such a system is really associated with altermagnetism, because we have shown conclusively the magnetic structure of the system is M prime M prime M, which can give rise to anomalous Hall effect due to barrier curvature. And that's a second conclusion we have reached. And the third conclusion we have reached is that when you apply a unilateral string, you can conclusively basically 100% detwin the sample to make it into a single domain. And therefore you can potentially really study the electronic properties sort of much better. And finally, we have shown that there's actually potentially there's clearly a sign change in anomalous Hall effect, which we believe is associated with altermagnetism and also associated with roughly the charge gap of the system. Yeah. So finally, we have discovered a new scaling regime that we don't really completely understand at this point. So now let me sort of move on to talk about the sort of a second part of the work that we were discussing. That this is basically done by Pengcheng Dai and Stephen Gomez. Alvarado. So this particular experiment is basically to try again to answer this very simple question. As I said earlier, that in terms of altermagnetism, it basically requires the local environment to be different between the nearest neighbor sort of manganese ions, and it should in principle be completely independent of the direction of the moment, right? As I mentioned earlier, the chromium antimony would have a moment along a C-axis, which is altermagnet, and then the manganese tellurium, which has a moment in the plane, but it's also altermagnet. But in the case of chromium antimony, there's no anomalous Hall, at least not in bulk, whereas manganese tellurium there is. So one immediate experiment we wanted to do is to basically ask the question that what actually happens if you dope lithium onto the manganese tellurium. And what's actually really interesting in this particular case is that if you dope lithium into a magneturium, and although the microscopic origin is not yet known, but if you dope lithium into the system, it has been shown conclusively by the Oak Ridge group that the spins of the system actually rotate from the in-plane direction to the c-axis direction. And also, for once you dope, actually the amount of lithium you can dope it is exceedingly small, about 3%. So once you dope it, from in-plane, rotate the system from in-plane to the c-axis direction, and then you immediately get rid of the, what's called, the domain issues, right? You don't have these three domain anymore. And in principle, all the conclusion in terms of outer magnets should not be actually affected by such a doping effect. But in reality, we find it to be quite different. And as soon as you dope the system, from a sort of a zero doping to 3% doping, there's actually a dramatic transition from essentially a sort of a semiconducting to a very, very good metal. Of course, we confirmed the situation that we confirmed the situation where the moment is really rotated along the c-axis. And in addition, that we found that previously people have done powder measurement have shown that you have a additional sort of gap opening at the gamma point, and now the anisotropy becomes larger. So we wanted to look at what actually happened to the spin wave spectra, for the battery. So for such a system, because in principle, it shouldn't really matter, right? I mean, whether the moment is along C or in the in-plane direction. So what actually happens is that we look at the entire spin wave. Both Stephen and Ting Jun have looked at the entire spin wave. We first confirm that the zone center, a spin wave gap open up when you dope lithium. But what's really surprising to us is that once you dope lithium, we find that even though the total exchange coupling constant reduced slightly, what really sort of surprised us is your Magnon bandwidth, your Magnon width, which is a lifetime of the system, actually increased dramatically, by roughly a factor of 2, a factor of 3, as compared with the resolution limited the case for the pure magneturium. In the pure magneturium, we can essentially think about the system is really sort of a local moment system, a Heisenberg sort of type of exchange interaction. But now, if you look at the Magnon width in terms of the figure on the upper right, you can basically see that the Magnon width increased by roughly sort of a factor of 2 or 3. So this is actually exceedingly surprising, because in any sort of insulating system, in terms of a Heisenberg model, you should expect that your Magnon damping should be strictly forbidden, because the Magnon interaction, in local moment systems are exceedingly rare. I mean, we're talking about collinear system, right? And in this case, we find that become much broader, and we speculate that this broadening, it could be due to really the fact that now you dope lithium into the system, it really induces sort of itinerant and local moment interaction that clearly broadens the spin wave, particularly near the zone boundary. So and in the case of ultramagnetism situation, that we still see the sort of it was the upper panel shows the splitting that's seen, and when we look at the neutron scattering, the splitting become broader. But I don't have the data from Ming's group. But Ming actually have done his group actually have done the opposite measurement, and the opposite measurement show the band splitting it really doesn't change between the undoped and doped case. So what does this mean? And this is again showing sort of the band splitting is more or less still present when you dope lithium into the system. So what does this actually mean? What this actually means is that if you really try to think about sort of ultramagnetism and try to understand the transport properties, you cannot conclusively and only think about the system as being a local or being an itinerant system. You really have to think about the system in terms of magnetism. You can more or less think about it as a local moment. But in order to introduce sort of itinerancy into the system, you really have to think about the magnets have to be interacting with itinerary electrons. And therefore, the system is actually much more complicated, than sort of the naive notion of, it's just you have an outer magnet, it will give you rise to an anomalous Hall effect. Yeah. And we can do sort of a local moment, sort of a sum rule, and basically shown that in both the lithium doped case and the undoped case, you can describe the whole system as basically being spin about 5 half. You don't change the moment much. So really sort of increase the spin wave boundary. Yeah. So this is sort of the conclusion that I have. Basically, there are two sort of messages in this study that the system is not really a simple a purely local moment system, and you have to really considering the itinerary electron and local moment interaction that give rise to additional sort of physics that hasn't been considered so far in the purely local moment outer magnet. Yeah, thank you.
Thank you. Very nice talk. So my first question is, I'm sorry if I missed it, were you ever able to use the strain to like directly switch domains in the ordered state, or was it always sort of like a strain cooling process?
Oh no, in the neutron scattering experiment, of course we always put a strain at room temperature, right? I mean, yeah, you can't. But basically, the strain effect is basically done with a device like this. Yeah, with a device like that, right? The crystal is in the sort of middle, the black portion of it. So we basically mount the crystal in there and then put a string on and then cool down, and then then we can take the string off and then compare the intensity differances, right?
But you're always cooling down through the Neal temperature.
Yeah, with the string on, Yeah, but in the transport measurement, that we actually fix the temperature and then sweep the string.
So you think you can switch?
Yeah. I don't think it matters. Yeah.
And then, sorry, second question on that is, do you know if anybody has done polarization on this, and does it agree with your conclusion of the direction of the moment?
What do you mean polarization?
Polarized neutrons.
Oh, no. I mean, this is hard enough. I mean, it's actually conclusive. You don't actually need polarized neutron for this. The reason you don't need actually polarized neutron for this, I mean, I didn't have time to talk about this. I mean, we have done we compared all the possibilities. I mean, we actually wrote like maybe 5-6 pages of supplementary material to try to discuss in detail the intensity changes in all the cases. I don't think you need polarized neutron because the Qs are once because you know the strain direction, the magnetic bright peak direction, the changes, right? And you don't really need polarized neutron for that. Yeah.
Okay, thank you.
I mean, the important thing is that we've shown you can apply strain in two directions, right? We have shown conclusively that the moment always is along the next nearest neighbor direction. It does not change as a function of a unilateral strain you apply. I mean, of course, I have to say that we only apply to whatever the screw. Yeah. But it's very small. Yeah.
Other questions?
Yeah, thank you for a nice talk. So for the anomalous hole, like strain tuning, beyond the detuning, do you think there are other, like for example, the gap tuning with strain?
I mean, gap, you mean the charge gap or spin gap? Charge gap?
Yeah.
I don't think the charge gap changes much. I mean, actually, we have those data. I mean, we haven't done. I mean, so far the temperature dependence is mostly done at the zero temperature, right? So once we've done the strain measurement, we typically always cool to the particular temperature and then sweep the strain. I mean, what you're saying is that whether we should just do as a whole temperature. I mean, we actually have those data. We have a take a look. Yeah.
And do you think there's anything beyond the detuning effect?
Oh, you mean strain?
Yeah.
Well, I mean, in principle, I mean, if it's due to sort of the barrier curvature effect, it has to somehow change the electronic structure of the system, right? I mean, but such electronic changes, structure changes is going to be so tiny, you guys won't be able to see.
I see.
Right?
Thanks.
Yeah.
Thank you, Pengcheng, for the very nice talk. Just wonder that this manganese telluride has this intrinsic magnetostriction property, like where you cool down and it has its own strain. When you applied the external strain with the device, I'm wondering if you have to make any consideration for the intrinsic magnetostriction.
Oh no! Like I said, I mean the magnetoelastic effect in the case of magnetotellurium is exceedingly small. Basically, when you put a string on, right, you don't change magnetization. You don't change M much at all. It's a 3 orders of magnitude smaller than the case of a manganese 310. So I mean, this is one particular. I mean, actually, Wei Liang, who's sitting there, has done a separate system, which is hexagonal iron sulfur, and which has a larger magnetometer. It's 1 order of magnitude larger, right? It's 1 order of magnitude larger than the manganese tellurium. So manganese tellurium seems to be the only system that has a tiny amount of magnetoelastic coupling, really suggesting that the effect that we're seeing is purely electronic. Whereas in the case of the iron sulfur, that Wei Liang had shown conclusively that the anomalous Hall reduction is proportional or roughly proportional to the reduction of the magnetization. Unfortunately, in the case of manganese tellurium, because stability already the stability loop is so small, we cannot do that in a squid to see whether there's actually a connection between that. It's actually an open question.
Any more questions? Okay, if not, then I have a question.
Yeah, sure.
Are any of these magnon modes having like a non-trivial Chern number associated to them? Or can altermagnets have, I don't know.
Well, in principle, I mean, if the band is split, right, your spin wave should expect to see, you should expect to see the chiral term, in turn, but that's never been seen. I mean, at least not in manganese tellurium. It's been seen in insulators, but this is sort of a fairly large challenge experimentally, mostly because you first have to detwin it, because once it becomes twin, then it's mixed, right? And then you have to put it in the polar neutron beam, which is quite hard. Yeah.
Okay. Yeah. If you have no more question, let's just thank the speaker.
Yeah. Thank you.